So today we're going to start talking about uniform circular motion. That is, what are the forces and interactions that are causing something to move in a circle? So uniform circular motion, UCM for short, is the motion of an object in a circular path at a constant speed. Yesterday we talked about the idea that there might be tangential speed. We're talking about today what happens when we just have a constant speed. So again, constant speed means constant magnitude, but the direction's changing, right? So the only acceleration that there's going to be is only centripetal acceleration. So I'm not going to have any tangential acceleration, just centripetal. This is kind of the definition of uniform circular motion, that it's moving around in a circle at the same speed. And really the force that's causing this is this net force of centripetal acceleration. So the centripetal acceleration will always point towards the center of the circle. Always, 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 always. Look, see, always, always. Since the acceleration is towards the center of the circle, the net force causing the acceleration must also point towards the center of the circle. And this one is important when you're drawing a free body diagram. Like if you're drawing it and you're looking at this and you're saying, my net force is not towards the center of the circle, then maybe we need to look back at the free body diagram and see like, where could we have adjusted this? Because we know that the net force must be towards the center of the circle. Okay, and then we call this net force centripetal force. But again, this net force that's causing this circular motion, we call it centripetal force, but it's really just any other force that we've talked about, like gravity or normal force or friction. Okay, so we call it centripetal force, and it's really important to never use the word centrifugal force on the AP test because there's no such thing. So sometimes you'll hear people say, this centrifugal force caused me to exit my car. Like if you've ever been on those amusement park rides where you somehow stand up and it spins and you end up getting sucked up against the edges. Sometimes it makes you go up. Like I remember the Gravitron does that. There's a couple of rides that do that. So when we're talking about that is not centrifugal force, right? This idea that if you spin around on a corner, right, that suddenly if I were not seat buckled in, I fly to the edge of the other side of the car. That's actually not even centripetal force. That's inertia, right? Like you are not attached to the car. The car has a force applied on it from the friction on the road that's causing it to go in a circle, but you don't have that force. You just continue in your inertia on your path that you were on, which is a tangent, right? So you continue as if you're going out of the car continues with that path. So that's really what's causing that is inertia and mass. So I tried to write this down. When you're a passenger in a car and the driver makes a hard left turn, your body wants to continue in that straight line because you have mass and inertia, not because of some magical force that some people, for some reason, called centrifugal force. It's not a thing, right? So the force that we're talking about is just centripetal force, that force that's causing it to go in the center. If you want to talk about why it is that your body wants to go in a straight line, that's just straight up inertia, right? You just always want to take the path that you were on and not change directions. Okay, so I know this is probably really hard to see from far away, so I'll describe it, and then also these notes are in the OneNote too. So this is just a circle and it's trying to show where are all the forces. So this motion is showing something clockwise. So you can see that at every point, if this is spinning in a clockwise direction, and I'll kind of underline these here, we have the tangential velocities that would go off. That's not really an underline. The tangential velocities would go off in each direction. If I'm saying I'm at this point or this point or this point, what's happening at each of these points? So this is a clockwise motion, and you, if you're in a car, would want to continue on this sort of tangential path, although the car has a force applied to it and it's going in a circle. Okay, so if you'll notice, all the forces are directed towards the center of the circle, all of them, because no matter where you are in the circle, if you are a car going in that circle, that force is directed in the circle, which means that you have some sort of centripetal acceleration that is also headed in that direction towards the circle. Okay, because the net acceleration has to be where the net force is. So all of that is directed towards the circle. This is very, very common to see on the AP exam. Okay, so a couple of things to note from this picture, that the tangential velocity is always parallel to the path and in the direction of the motion, and that your centripetal force and centripetal acceleration are perpendicular to that tangential velocity. All right, so basically, oh, hey, look, we got a lovely 90 degrees here. It's lovely. Okay, force towards the center, tangential velocity perpendicular to it. And some form of this picture seems to always show up on the AP exam, so it's a good one to kind of know this idea of where are your forces, where your acceleration, where would your velocity be. Now we're going to move into formulas. So yesterday we talked about concepts, right? We talked about, we spun the water upside down, and we taped, we tied string to that car and taped it to the table, and we saw how it moved around. We saw that when we cut the string, it went in a tangential velocity. We spun the medicine balls around, right? So we were able to see concepts of this idea that a force is pointed center, but we didn't do any kind of math with it. So this is the equation for it. So we have centripetal acceleration, A sub c, is tangential velocity squared divided by the radius. What's great about this formula is it's on the AP exam on your formula sheet. Okay, where AC is the centripetal acceleration, VT is the tangential speed, and R is the radius of the circle. If they give you the diameter, you're going to have to divide it by 2 to get the radius. Then the direction of the acceleration is perpendicular to the direction of the tangential speed, right? And maybe I worded this awkwardly, but what I mean is the direction of the acceleration is always towards the center. So the acceleration should be towards the center of the circle. And then the tangential speed should be perpendicular to that. So this is how we can find centripetal acceleration. Now, when things spin in a circle, we have different terms for the way things spin and how they spin. So we've got these terms called period and frequency. So period is how long it takes an object to make like one full circle of a rotation. So if I'm talking about this record player here, which is probably a thing that you may or may not have seen in your life, but if I want to go for a whole spin of the record player, it'd be like, how long does it take from this point right here to go all the way around in the circle and come all the way back? That would be period. So how long it takes to go in that one circle. And period is symbolized with a capital T, and it's written as seconds per revolution. So how many seconds does it take per one circle? Makes sense? Frequency is different. Frequency is how many times an object goes around in a circle every second. So this is how many revolutions, if I go 1,000, how many times does that record spin around? Sometimes you have period, sometimes you have frequency. Frequency gets a little f, and it's revolutions per second. So you can kind of see the gist of this. Oh, hey, look, this is their relationship. Period is the same as 1 over frequency, or frequency is the same as 1 over period. So sometimes you're given the period of something that's spinning, sometimes you're given the frequency. These are terms that I want you to know just so that you have an idea of what the difference is, and we'll see them more and more. Are these formulas given to you? Absolutely not. These are things that they expect you to know. So at least you got one, I suppose. So for tangential velocity, now that we know about period and frequency, we can talk about tangential velocity. So we know velocity is just distance over time, and we're talking about moving things in a circle, right? So our distance is our circumference of the circle, 2 pi r, and our time is our period, like how long it takes to go 1 revolution. So we symbolize that with this capital T action, period. So my tangential velocity is 2 pi r over t. Okay, now if I don't have period and I have frequency, I can say that it's 2 pi r times f, frequency, right? Remembering that this is period and this one's frequency. Do we get this one on the exam? Absolutely not. No, but you know that velocity is distance over time, and they do tell you that the circumference of the circle is 2 pi r in the geometry section of the formula. So you can infer it, but you have to really think about this. Okay, so not ideal, but there we go. All right, so now we're going to talk about the centripetal force. So this is the force that causes an object to move in the circle. And like I said before, the important thing to know is that centripetal force can be gravity, it can be tension, it can be a normal force, it can be friction. It's the forces that we've always drawn on free body diagrams. In fact, we aren't even going to label them as centripetal force. We're going to label them in our free body diagrams as gravity, tension, normal force, friction. And then we just know if it's going in a circle, it's going to be the centripetal force. So when we write equations, we would say that as F sub c. And our centripetal force is our net centripetal acceleration, right? So that's m times a sub c. Now, we already talked about centripetal acceleration, and that is one of the things that you actually get. And that is velocity squared over r. So if I plug that in for a, then I get this centripetal force is m times v squared over r. Again, this is something that you can derive. At least you get this one here. And then you can plug it into F equals ma, just knowing that this is going to be one that we will use a lot. All right, so that's centripetal acceleration, or how we plug in centripetal acceleration into centripetal force. Classic AP question here. How much work does the centripetal force do in 1 complete revolution? So in order to think about that, we need to go back to our formula of work, which is force times distance cosine theta. And we need to think about what is the distance here, what is the force, what would theta be, in order to think about how this would work, how much work could be done for centripetal force in 1 complete revolution. So I want you to think about this with your neighbor friend. And chat for a bit, and I'm going to ask you to pause the video so that you can chat for a bit, and then we can come back. Okay, so we need to think about where is the force and where is the distance. So if I'm drawing a circle here, right, and my force goes like this, but at any given point, instantaneously, this thing is moving in this direction. Right? The tangential velocity is perpendicular. So that means I'm taking cosine of 90 degrees. Oh, hey, that's not going to work. So classic trick question here. because we know that the instantaneous direction is perpendicular to the force, we know that theta is 90 degrees. If theta is 90 degrees, cosine of 90 is 0, which means no work is done. So if it asks you how much work does the centripetal force do in one complete revolution, the answer is 0. It does 0 work, no work whatsoever. Super tricky. So now we're going to get on to how do we solve for centripetal force. So the key thing is to use F equals the net force, right? I want to know what my net force is. And I know that my net force, right? So I'll write this here so it's a little easier to see, right? My net force is mass times acceleration, and I'm going to use that to solve for my centripetal force. So step 1, always draw a free body diagram. Label all of the forces. Never label them force centripetal. Instead, say it's friction, normal force, gravity, tension. These are the forces that I want to see. I do not want to see F sub C on a free body diagram. Right? That's our net force, is essentially our force, our centripetal force. Okay. Then when choosing which directions that we want to break components to, right? How do we do this? You always need to make sure that you're orienting it. So one of the directions is the direction of the centripetal acceleration. So when you're thinking about how am I going to lay out my X's and my Y's, yes, there's going to be components to this. Then you need to think about, make sure that you have centripetal, one of the directions in centripetal, the direction of centripetal acceleration. Okay, what kind of problems will I get with these? Well, some are nice. Sometimes it's a single force that causes the circular motion. That's nice. That's rare, but that's nice. We like that one. Number 2 is a little bit more common. We have a component of a force is causing the circular motion. So we're talking about trig here. Cosine of something or sine of something is causing the circular motion. And then we're not going to get to this today, but sometimes we have combinations of forces that cause the circular motion, and we'll get to that one tomorrow. That would be how your water stayed in your cup, would be number 3. Okay, so I expect that you can't really see these from far away, but we're going to look at examples of single forces causing circular motion. So I'm going to read it out loud because the font is way too hard for you to see. But example 1 is the Earth going around the sun. Example 2 is a car going around a turn. And example 3 is an amusement park ride. You know, that one that I was talking about where you spin and spin and spin and you stick to the edges and you're like, whoa, I'm stuck to the edges. Whatever that's called. In my day, it was called the gravitron, so whatever it's called. So draw a pretty picture that shows those 3 things. And I'm going to give you a second, because what I want you to do with your neighbor friend is, once you have these pictures drawn, I want you to draw a free body diagram for what is the force acting on this to cause the circular motion. Right? So I've given you hints. I've said when the Earth is going around the sun, our centripetal force is gravity. For example 2, when we have a car going around a turn, the centripetal force is friction. That's right. That would be the tires on the road is what actually keeps you on the road. Because when there's ice, you can't stick to the road and you just slide off, right? So it's friction is our centripetal force when a car goes around a turn. And then example 3 is actually if you think about it, you're stuck to the wall, right? So this one, I'm giving you hints on this. We have our centripetal force is our normal force. So the force of you, the wall on the interaction between you and the wall is what's actually making this centripetal force. So I want you to draw where these forces are with your neighbor friend. So go ahead and pause the video, and then we will come back to see these drawings. Okay, and we're back. So there's our force of gravity. This one should be really simple because I told you what all the forces were. You literally just had to draw arrows. But when you're thinking about how would you do this in an equation, right? And I'll make these bigger because again, I know they're super hard to read. You want to think, okay, my centripetal force is gravity in this case. So not only do you have to draw a free body diagram, but you have to write out like how would this equate to each other. So this first one is I'm going to say that my sum of my forces, I'm always going to start with this, equals MA. And in this one, I know that my sum of forces, my centripetal force, is actually my force of gravity. And I know that that's equal to my centripetal force, so that's equal to mv squared over r. So you're probably like, what, Ms. Shope? Well, if you think about it, force of gravity is the centripetal force. So force of gravity equals the centripetal force. Now that you know how to do that equation, you should be able to do the rest in example 2 or 3 in your head for a sec. So I'll give you a sec to think about that, but maybe without pausing the video. And let's go on to friction. So friction, that's the direction it would be in if you are turning in a pretty circle or a curve on a road. And then again, I'm going to start with my sum. Whee! Okay, so my net force is going to be equal to MA. Then again, because I've told you that the centripetal force is friction, I'm just going to say, all right, so the force of friction is my net force. And I know that my force of friction is going to be equal to my centripetal force, so there you go. And then I can go even further and plug in what I know from my force of friction. My force of friction is just mu times my normal force, right? So this is how we're going to solve the equations, is by doing free body diagrams. Looking at example 3, we have our normal force, and I would just say my normal force is equal to my centripetal force. So you've got this down now, and you have the general idea of how we're going to do this. This is the nice single forces. So we're going to move into more complicated forces. Here we go. Okay, so now we're going to talk about force components causing circular motion. And this is more difficult. Not going to lie, this is more difficult. So this one is a ball on the end of a string being spun around in a circle. So you're just going to draw a ball on a string being spun around in a circle. However best you can draw that. Okay, and I want you to try to draw what are the forces acting on this ball. So again, it's tied to a string that's being spun in a circle. What are the forces acting on this ball? Draw a free body diagram and then check it with your neighbor friend. So why don't you go ahead and pause the video so you can work on that problem. And then once you've got it, we can come back. Okay, so we've got some forces that I think you immediately recognize, right? We have tension. Tension is going to be going up because you're on a string. So we've definitely got tension. And the other force that you know we have is gravity, right? So we've got tension and gravity. And those are really the forces that are interacting. And that's probably what I would draw on the free body diagram. But we need to know what is making it go in that circle. And in this case, we need to look at the components of tension. Right? So I really want to think about if my circle is here, I want to think about what's the force that's going in this direction that's causing it, and I shouldn't draw it like that, but the force that's going in this direction that's causing it to go in that circle. So that's going to be perpendicular to my force of gravity, so it's got to be a component of the tension. So I'm going to put them in the two components, right? So I have, if I'm doing this, with the way that theta is there, that would be tension sine theta would be in my x direction, and tension cosine theta would be in my y based on where the angle is and how we're holding this. Okay, and I just drew the pretty picture to show you, oh look, it would be the sine and that would be the cosines, you can see it. So if those are the components, then I can start looking at the equations. So this is all the forces that are acting on this, but I need to think about the fact that this is the force that is causing the centripetal acceleration. So I need to have one of my forces there, and then I need to think about these forces as well. So my forces in my x direction and my forces in my y direction. So I know that it should be going around in a circle, so the net forces of my y should be 0. They should be canceling each other out, right? So that one's pretty straightforward. I'm going to say they have to equal each other. Very nice. Okay, so that's in the y direction. Then if I look in the x direction, I know that the net force in the x direction has to be equal to the centripetal force, right? So I'm going to say, okay, well, my force in my x direction, tension sine theta has to equal my centripetal force, m velocity squared over r. And that would be how we could start setting up equations to solve this problem. Then I could say I could use systems of equations if I wanted to, if I don't have tension, and I can solve tension for one and then plug tension into the other, and I can find theta, or I could find velocity or radius. That's a very common thing that happens is we have to solve one for tension and plug the other one in. This is the last example we're going to do. So we're looking at a car going around a bank turn. And again, you can draw a pretty picture. And we want to draw what are the forces acting on a car going around a banked turn. Okay, so take a second, draw a really pretty picture. You can see how pretty mine is of a car going around a banked turn. And then draw the free body diagram and check it with your neighbor friend. So go ahead and pause the video, and then when you think you got it, you can come back. Okay, we're back. So looking at this, there's some forces that I know you know. Gravity is going down. You also know normal force, right? Has to be perpendicular to the surface on the bank turn. So if I'm looking at this, I know that I need to look at the components of the normal force, because essentially what's keeping it in this circle has to be something that's pointed towards the circle, right? Right now I don't really have anything pointed towards the center of the circle. So I'm going to look at the components of normal force, and in this particular one, because of theta, this is cosine, that is sine. Beautiful. There it is. Okay, so those are my components. So if I'm looking at this, now I have, oh, okay, this is my centripetal force. This is the force that's going in the circle, and this is in the y direction that I need to deal with. So similarly, kind of like I did before, I know that my sum of my forces in the y direction have to equal 0. So I'm just going to set those equal to 0. Normal force times cosine theta has to equal mg. And then again, kind of like we did before, I know that the net force in the x direction has to equal the centripetal force because that's the thing that's causing it to go in a circle. So the normal force sine theta has to equal mass times velocity, tangential velocity squared over r. Okay, and again, if I don't have normal force, I can solve for normal force. I can solve like this equation for normal force, and I can be like, ooh, normal force is mg over cosine theta, and then plug that in over there. And then when I do that, when I plug that in over there, I want to show you something fun, because this happens a lot to us. I have mg sine theta over cosine theta, which means I just have mg tangent theta, right? So I feel like we end up doing this a lot. So remembering that sine over cosine is in fact tangent. There you go. Okay, the rest of the period you have to work on another mastering. And this one is a little bit harder because it has component forces on it, but you got this. You can work together. Bye.